Good evening, guys. Welcome back to Wisdom Academy YouTube channel. You are watching Wisdom Marathon series. So I'm very sorry first because the last live streaming was stopped in the middle due to the prevailing conditions in the city, like due to the rain. We don't like the power backup was not there. And suddenly the power went. But let us come back to where we were, and we were learning about the electric field and charges. And up to now we have seen what is the basic properties of charge. We have seen what is the Coulomb's law. We have seen the dielectric constant. We have also seen what is Coulomb's law in vector form. Solved a few questions based upon that. And then we learned about continuous charge distribution, where we came to know that there are three kinds of continuous charge distribution, namely linear charge density, you have surface charge density, and you have volume charge density, which is denoted by lambda, sigma, and rho. Now you are going to learn the next topic in this chapter, which is electric field. So I hope all of you have joined. Those who have not, please come and join. And those who have joined, please put the attendance in the comment section by putting a hi. Right. So, electric field, I was talking about it, and I said that it is the space, or it is the area, it is the region around any charge where its effect can be felt. So suppose I have a charge here, and up to what distance around the charge, if I bring some other charge, it will get attracted or repelled. That space around the charge is known as its electric field. Now, theoretically, to say electric field is infinite, there is no limit up to where electric field can go, theoretically. But practically, electric field do have a limitation, and it has a certain distance. So if I want to define what is electric field mathematically, I would define it based upon some test charge. For example, if you have a magnet and you want to find its magnetic field, what do? You bring another magnet, or you bring another magnetic substance near to it, and check if I keep it here, it is getting attracted or it is getting repelled. So you want to have another piece of magnet or another piece of magnetic substance to check whether a particular magnet, up to how far it is having magnetic field. Same way, if you have a charge and you want to find its electric field, you must bring another charge near to it, and that charge is called as test charge. So another test charge, if I'm writing it as q naught, it is brought near to it, and then what is the force acting on this charge per unit test charge, that is known as its electric field. That is, mathematically, electric field is given by force per unit test charge. So from here, very clearly you can understand two things. One thing is electric field is a vector quantity. Another thing is its SI unit. Its SI unit would be Newton per Coulomb. So same way, you can even find that the direction of electric field will be same as the direction of electrostatic force. So from here we have electrostatic force is equal to q naught into E. A very famous relation, will be helpful for you in many other questions also. So that is about the electric field. So electric field, to find the electric field, you must have a test charge. Without test charge, you cannot find the electric field. And if you ask me, sir, what if I have many charges? So what will be the electric field? Electric field due to one charge is F by Q. If you have multiple charges, then it will also increase. That is, before that, I will tell you that due to one point charge, due to a single point charge, what would be the electric field? We can find it very easily, because E is equal to F by Q. So if you have a single charge and you bring another charge, it will become equal to F by Q naught. I'm writing the magnitude of it, F by Q naught. And what is F? F for these two charges will be K. And if this is Q, it will be Q into Q naught by R square, and already Q naught is there. These two gets cancelled, and you get electric field as KQ by R square. So this is the formula for electric field for a single point charge. For a single point charge, electric field is equal to KQ by R square. Now, I was telling about a system of charges. That is the principle of superposition. If you have one charge here, the charge here, the charge here, and you want to find what is the net electric field due to all these charges at this point, then suppose it is Q1, this is Q2, and this is Q3, present at a distance of R1, R3, and this is R2. So the net electric field at this point X, if I want to find what is the electric field at X, that will be equal to E due to the first charge plus E due to the second charge plus E due to the third charge. So from here you can see very clearly it will be equal to K Q1 by R1 square plus K Q2 by R2 square plus K Q3 by R3 square. But please pay attention, electric field is a vector quantity. So never forget that you will not do the algebraic addition of all these things. You will do the vector addition of all these things. You will do the vector addition. Now, if you ask me what I am meaning by this vector addition, I'll tell you. Suppose I have taken a case. I am taking a case that I am having one charge here, positive. It is having some Q1. I have another charge here, again a positive. It is having Q2. And I am finding what is the electric field present at this point, which is at a distance of x, and suppose this distance is 2x. I'm just assuming. So first of all, if you place a test charge at this point x, this is the point x, and I'm going to put a test charge q naught. If I'm going to put a test charge q naught here, the electric field due to q1 would be in this direction, and that will be equal to E. I'm writing E1. So why do I take the direction of electric field in the repulsive direction? It's very simple. It's because when I bring a unit positive test charge, positive will repel. Same way, if I have a positive charge even here, this will also repel, and we have the electric field direction. I said you that F is equal to QE, direction of electric field and direction of electrostatic force is always the same. So if it is always the same, then obviously the direction of electric field is this, and direction of electrostatic force is this, and electric field also will be this. So what I will do, I will find the vector addition of all these two things. So I need to find what is the angle between them, theta, and then the E, if I want to say the E resultant of these two, will be the vector addition of E1 plus vector addition of E2. That is, it will be root over E1 square plus E2 square plus 2 E1 E2 into cos theta. I hope you remember this. This is the vector addition. So you can find what is the net electric field, what is the magnitude of net electric field, and that will be equal to E1 square plus E2 square plus 2 E1 E2 cos theta under root. So this is about the electric field, and this is about the principle of superposition. So as per the principle of superposition, net electric field due to all these charges will be the vector addition of all the electric fields. Right. So if I go to the next topic now, after learning about electric field, let us take a question now from the electric field. The question says like this: 2-point charges plus 8q and minus 2q are located at x is equal to 0 and x is equal to L respectively. The point on x-axis at which net electric field is 0 due to these charges. This kind of questions are very common. So if I'm right, this question has been taken from the sample paper given by the Cbse this year. Cbse has given a sample paper 2020 and 21. In that, this question is there. 21, 22, I think. This question is there. So a very important question, but very simple one. So there are 2-point charges plus 8q. If I just see what is the value of it, it is plus 8q and it is minus 2q, and they are located at 2 points. So on the x-axis, if I want to write, it is located at, suppose this I am taking it as x is equal to 0, and this point is x is equal to L. So what is present here? Here I have plus 8q, and what is it here? Here I have minus 2q. So I have plus 8q and minus 2q are charges present at x is equal to 0 and x is equal to L respectively. Now you please pay attention here. They are asking you to find any distance between there, somewhere, anywhere. Let me assume it that distance of the point where the electric field will be 0 to be at x from 8q charge. If it is at x, then remaining distance would become L minus x. So if the electric field is 0, see, the electric field due to plus 8q charge would be in this direction, isn't it? And electric field due to minus 2q charge, that will also be in the same direction. Are you able to feel? Because minus 2q here plus q naught, I'm keeping unit positive test charge, it will attract. So both will get attracted. I mean, this will get attracted, this will be giving a repulsive force on this point. So at this point, if I take this point as O, both E1 and E2 are in the same direction. So for the electric field to be 0, what will happen? E1 would be equal to E2. And what is E1? E1 will be equal to K into 8Q by x square, and this side I will have K into 2Q by L minus x the whole square, isn't it? So the net field is 0. And then Kk gets cancelled, Qq gets cancelled, you get L minus x the whole square divided by x square is equal to 2 by 8, that is equal to 1 by 4. And finally, you will get L minus x by x is equal to 1 by 2. So 2L minus 2x is equal to x. So x equal to, from here you can take, it will become 2x. So I can say very clearly that the answer would be equal to 2L. So a very simple question, you see. So next we are going to the electric lines of forces. So what are electric lines of forces? What are the properties of electric lines of forces? So again, if you pay attention, you will come to know that electric lines of forces are very much similar to magnetic lines of forces, which was taught to us in 10th standard. So there we learned that magnetic lines of forces are some imaginary lines which are present around the magnet and which gives us the idea about direction of magnetic field. Very similar to it, if you have charges, they will have electric lines of force which would give you idea about its electric field. So electric lines of forces are very basic. Like for example, if I have q charge, that is positive plus q, then it will have a radially outwards electric lines of force like this. So electric lines of force gives you an idea about how the electric field property are. If it is a minus q charge, the electric field will be radially inwards. It will be radially inwards like this. If I have one charge here plus q, another charge here minus q, that is, I have unlike charges which are attracting each other. So we know very well that if you have a negative charge and a positive charge, then the electric field lines goes from positive towards the negative. So it starts from here, enters here, starts from here, enters here. Like this it goes, like this it goes, like this it goes, and enters here like this. Not only that, it will be found that it will be like laterally bulged. It will be bulged like this, the electric lines of forces. See, sometimes we have questions from this lines of forces. So you need to be very clear. You need to be very clear, and then only you will be having an idea. So one student is asking that, yeah, yes, exactly. It would be magnitude of E1 only. We have to consider magnitude of E1 is equal to magnitude of E2. Very correct, you are saying. That is true. In the previous question, I think. Fine. So if I am coming back to this question, if you see the electric lines of forces between this plus q and minus q, it is bulged in the inward direction. I mean laterally direction. If I have two charges, suppose I have here plus q, another charge plus q, which are repulsive in nature, you will see that their electric lines of forces would be like this. It will be going outwards like this. So if I just draw the contour, I will find that it is elongating in this direction towards the charges. It was elongating in the lateral direction. So the elongation when the two charges are dissimilar is in the lateral direction, but when they are similar, it is in the linear direction, in the direction of the charges. So that is very important to know about different kinds of electric lines of forces for different cases. So I have still not gone into the properties of them. I'm just telling you what are electric lines of forces, and for different charge conditions, what are those. So if I go to the next page now, to just know about the properties of electric lines of forces, then you will come to know, and you can just note it down, because I have seen some questions are there directly coming from this part also. So some very basic things, that what are the electric lines of forces property. The first one is, as you know very well, they are imaginary. They are imaginary. So electric lines of forces are the imaginary lines of forces. They don't exist really. They are just the imagination, which gives us an idea about electric lines of forces. The second point is about how they start and how they terminate. So I said you in the previous page itself that they start from positive charge. They start from positive charge and terminate in negative. And terminate in negative. This is the second important property of electric lines of forces. Then they always, I mean, if you keep a positive charge, it always follows the path of electric field. For example, if I have electric field in this direction and I keep the positive charge here, it will move in this direction. If I keep the negative charge here, it will go in the opposite direction. So remember that positive charge, I'll write the third point as positive charges follows the path of electric field. Follows the path of electric field. And obviously, the negative charges will be against the direction of electric field. You can see very clearly from here. The fourth point, we all know very well that if you draw tangent to the electric lines of forces, it will give you the direction of electric field. So tangent drawn to electric lines of forces will give you its direction. So what is the direction of electric field? That can be easily found out by the tangent drawn to any electric lines of forces. Next thing is, yeah, they cannot intersect. Electric lines of forces never intersect, because if they intersect, then at same point you will have two different directions of electric field, which is not possible. So electric lines of forces, they will never intersect. Another important point I can write here as how much close the electric lines of forces are, that much strong is the electric field. So strength of electric field. Next point is about strength of electric field is judged by the closeness of electric lines of forces. You don't need to confuse what is ELF, that is electric lines of forces. Another point about the electric lines of forces is that, see, very important point again, I have seen question coming from this point alone, that electric lines of forces are always perpendicular to the positively charged plate or negatively charged plate. If I have a positive charged plate like this, then electric lines of forces will be in this direction, perpendicular outwards. If I have a negatively charged plate like this, then electric lines of forces will again be perpendicular towards the plate. I hope you're understanding this, that electric lines of forces are perpendicular to positive and negative charged, I should say, plates. So if you have negatively charged plate or positively charged plate, the electric field will be perpendicular to it. Remember that. One more important property about electric lines of forces is that electric lines of forces will never pass. It will never pass through a conductor. So yeah, ELF is electric lines of forces. Exactly, that's what I told you. So ELF is electric lines of forces. So ELF is not different. So again, Prasanna is asking, sir, does a field line exist in 3 dimension also? Obviously, Prasanna, if I have a charge plus positive charge, then the electric lines of forces will be radially outwards. The meaning of radially outward itself is 3 dimension. It will not be only in 2 plane. It will go here, it will go here, it will go here, it will go everywhere. So electric lines of forces are 3 dimensional quantity. I hope I have cleared Prasanna's doubt. And that informal Tamil, for that person also I have given that yes, ELF is electric lines of force, and electric lines of force represent electric field. So you are asking whether ELF is same as electric field. ELF is not same as electric field. Electric field is force per unit charge, but electric lines of forces represent the electric field. I told you, if you draw a tangent to electric lines of force, it will give you the direction of electric field at that point. So they are not same, but yeah, ELF, that is electric lines of forces, represents the electric field. I hope I could clear. So I am coming back to the next property, that is it don't pass. So electric lines of forces never passes through the conductor. Never passes through the conductor. And one more thing, they will pass through insulator. That also should remember. So 9th point I will write as electric lines of forces passes through insulator. So electric lines of forces, they don't pass through conductor, but they pass through insulator. So all these points, I hope you have understood it. I have told step by step everything. They are imaginary lines. They start from positive and terminate towards negative. Positive charges follow the path of electric field, and negative charge will go against the electric field. Tangent drawn to any electric lines of forces will give its direction. They will never intersect each other. Their strength of electric field will be purely given by the closeness of lines. If the lines are too close, electric field is very strength that is very strong. So you may expect a question in the board examination. They will draw 3-4 diagrams. Just by judging the closeness of electric lines of forces, you have to tell which material has higher electric field, so that you can understand, I think. Then electric lines of forces are always perpendicular to the charged plates. I mean, if it is positive charged plate, it will be perpendicular outwards. If it is negatively charged plate, perpendicular inwards. Yeah, and they never pass through conductor, and they always pass through insulator. These are the basic properties or the properties of electric lines of forces. If I go to the next topic now, that is about electric dipole. Electric dipole is the arrangement. So it is not a property, it is arrangement of two charges. So if I take two charges and if I arrange them in such a way that these two charges are equal in magnitude and separated by a very small distance. So if I take one charge minus q, sorry, yeah. So if I take one charge as minus q and if I take one charge as plus q, so they are having equal magnitudes but opposite charge. That is, they are equal and opposite charges. So when two equal and opposite charges are separated by a very small distance. So in the board, I'm drawing it as a big distance, but in reality, dipoles exist in very small distance. So even the strength of the dipole, it purely is governed by distance between them. So we want, I mean, if I write about the ideal dipole, we want ideal dipole to have very large distance, very small distance and charges to be very large. Remember this. So the distance I'm taking it as 2d, and I have explained it to you why this 2d is taken. I can take it as d also, but it will help me in the derivation. Definitely, I'm not going to derive now how to find a dipole moment for various conditions, but you will come to know that if you find the dipole, the electric field of electric dipole at an axial point and at an equatorial point, you will get to know why I'm taking 2d. That is there. You can even see my previous video for that if you want to have a reference. So 2d is the distance of separation between them. So if you want to define what is electric dipole, it is the arrangement of two equal and opposite charges separated by a very small distance, 2d. And we want always ideal dipoles. Any ideal dipole, I want it to have, ideal dipoles should have large charges charges and least distance. Least distance. So we want distance to be very less and we want charge to be very big. So we want dipoles to be like that. So ideal dipoles are like this. Moreover, you should also know that dipole moment. What is dipole moment? It is represented by P. It is a vector quantity. It is represented by small p. It is the, if I define dipole moment, I would say it is charge times the distance. So if you take any charge, I should say the magnitude of charge, q multiplied by the distance, that is 2d in this case, q into 2d will give you the dipole moment. And direction of dipole moment is from negative towards positive. I'm always saying this to you. Please keep in your mind. P cap is the direction. So direction of dipole moment is from direction of dipole moment is from negative towards positive. Remember this, because in chemistry you have just the opposite of it. So the direction of dipole moment is from negative towards positive. Very important point. So let us go to the next page. After knowing what is dipole moment, let us try to find what is the electric field due to the dipole moment. That is due to the at an axial point, at an equatorial point. When I say axial point, see, I have a dipole like this. I have the dipole something like this. Minus q is there and plus q is there. So I have two equal and opposite charges separated by a very small distance. If I take an axial point, means any point on this axis, here, on this line, or anywhere. So suppose if I'm taking it at a distance of x from its center. From its center. Center means if this completely is 2D, obviously you are understanding that this distance is d and this distance is also d. So I am taking a point, let this point be x. I am taking the point x in such a way that it is x distance away and it is away from the center. Don't forget that. So already we have derived it in the previous sessions and we have found that the electric field due to the axial point, it would be equal to k, that is 1 by 4 pi epsilon naught times of 2p, 2 into p into x, actually p is vector, into x by x square minus d square the whole square. Remember this, it is 2px by x square minus d square the whole square. This is the formula of electric field due to an electric dipole at an axial point. One more thing, if this distance d is very small and it is that much small that it is like very less compared to x, then if you solve it, you will get the value of E axial as k into 2p by r cube. Of the direction should be, if I write a direction, it should be same as direction of dipole moment. See here, if you see here itself, you can realize that positive charge is there and here negative charge is there. If I want to find the dipole moment at electric field at this point, I will keep a unit positive charge q naught. This will give a repulsive field. This will give an attractive field. Since the repulsive field will be higher than the attractive field, the net field will be in this direction. That is the direction of dipole moment, because from negative towards positive, this side, from left towards right. So I am writing the direction as p cap because it is from negative towards positive in a direction. So this is about the electric field. So two formulas I have written. One is a general formula, which is very important, and this is the formula for a scenario when your dipole or when your dipole's length, that half of the length d, is very much smaller as compared to the distance at which you are finding the electric field. Now if I take an axial point, so axial point means, see, if this is minus q and this is plus q, this is their axial distance. What is the equatorial distance? So whatever I found here, it is at an axial point. This was at axial point. Same way I can talk about the equatorial point. I can talk about the equatorial point. So what happens in the case of equatorial point? So if I take a equilateral point, it is negative q, positive q, it will be perpendicular to it. So from center, this total distance is 2d, total distance is 2d. So from the center, if I take that x distance away, at this point, let it be x, I want to find what is the electric field. If you solve and find, you will come to know that electric field at that equatorial point is equal to, when I solve it, it will become equal to k into p divided by, it will be x square plus d square, x square plus d square power 3 by 2, x square plus d square power 3 by 2. Not only that, same way here, if d is very much less than x, you will get E equatorial is equal to k into p by r cube. Once again, if I want to tell you about the distance, direction here, see, negative and this positive will give a field in this direction. This positive will give a field in this direction. So the net field will be in this direction, isn't it? Net field will be, see, direction of dipole moment is here, P. So direction of the net electric field will be in the opposite direction to the dipole moment. That's why direction I'm writing it as minus P cap. Remember this, minus P cap. So why I'm writing minus P cap? Because it is having a direction exactly opposite to direction of dipole moment. Remember this. So this is about the electric field due to electric dipole at an axial point, at an equatorial point. Both I have discussed. Let's go to the next page. So, okay, one question based upon that. If even be the electric field, once again, one question has come there. So Kritika is asking, at the condition D is very less than X, can we say it is an ideal dipole? Yes, Kritika, you can say it is an ideal dipole only if the charges are huge. So in a question, if they have given you that there are two charges, usually if you remember the questions of dipole moment, they will give microcoulomb as the charges. So if they give you, we have 20 coulomb or we have 500 coulomb, minus 500 coulomb plus 500 coulomb, and distance is very small, then you can take it as ideal dipole. So in this ideal dipole case, distance is not only the condition but also the charges value. So if it is a sufficiently bigger charge, if it is in some millicoulomb range or coulomb range and a distance is in nanometer range, then it becomes ideal dipole. So for a dipole to be called as ideal, distance should be very less and the charges should have a higher value. I hope I could clear doubt of Kritika. Let us come back. So if even be the electric field strength of a short dipole at a point on its axial line and E2 that on the equatorial line at the same distance, then what? Okay, this is a simple question. We know very well that the formula of E axial, that is for the condition if D was very much less than X. E axial was K into, I'm writing only the magnitude now, K into 2P by R cube. And for equatorial, it was K into P by R cube. So very clearly we can see from here that E axial is 2 times E equatorial. Simple question. And they have given here E1 to be axial and E2 to be equatorial. So obviously E1 will be equal to 2EQ. A simple one. E1 is equal to 2EQ. Yeah, even this kind of questions can be expected. So where you can score your marks. Never forget that. Okay. So coming back to the next question. So a point P lies on the perpendicular bisect of an electric dipole of dipole moment P. Fine. So they have given the value dipole moment as P. And what else they have told? They have told that if the distance of P from the dipole is R, that is much larger than the size of the dipole, then the electric field at P is proportional to what? Okay. So one thing they have told very clearly that R is much larger than the size of the dipole. So when they have mentioned this statement, that is, here they have taken that X is very much bigger than D. Obviously, D is less than X or X is more than D, both are same meaning. If that is a scenario, then we know very well that it is a question of equatorial, isn't it? So because perpendicular bisect of this thing they have written. So we know the formula E is equal to K into P by R cube. So very clearly we can see from here that E is proportional to P and inversely proportional to R cube. So obviously P will be proportional to P and inversely proportional to R cube. So B is the answer. Again, a very simple question Don't expect this kind of questions in the examination much. If it comes, your luck. Fine. So next, I'll go to torque on electric dipole in electric field. So if you have an electric field and you keep an electric dipole inside an electric field, for example, if I have a field like this, I have two possibilities, that the electric field be a uniform electric field or it may be a non-uniform electric field. So first I am taking uniform electric field. So if I have uniform electric field, and in this uniform electric field, if you are placing a dipole like this, minus q plus q, obviously dipole moment in this direction, p. So what will happen? We know very well, any charge in the electric field will be subject to a force, F is equal to QE. And for plus q, it will be acting in this direction, F of plus q. And for minus q, it will act in this direction, F of minus q. Now, you have to find what is the torque acting on it. See, when there is any object, you say, in this case it is dipole, and we are given two forces which are acting in the opposite ends in such a way that they are equal and opposite, they will make it to rotate. So if it is equal, then the net translatory force will be 0, that is no translatory force, but torque will be there, which you learned in 11th class itself. So this F plus q and F minus q being of equal magnitude and opposite in direction will create a torque inside this, and that torque value, tau, it is a vector quantity obviously, is equal to dipole moment cross electric field, or I can say torque's magnitude is equal to Pe sine theta. Obviously n cap will be there. Torque will be equal to Pe sine theta. It's a very important thing. And if you have a non-uniform electric field, there is also possibility that we have a non-uniform electric field. So non-uniform electric field is there. Then in addition to this torque, you also will have the lateral, translatory force. So something like this, there is some electric field which is not uniform. So here I had same, F was same for plus q and minus q. Here I will have F1 for plus q and I will have F2 for minus q. So I have unequal forces acting in opposite directions. So if you have unequal forces, definitely it will make it to not only rotate but also to move. So it will go like this, it will go like this, it will start moving. So it will have a rotatory force and translatory force. So this dipole will start moving. So you can imagine something like this. It is going like this. It will keep on moving and going front, something like this. So you can expect question from here also. So in non-uniform electric field, it will roll, I should say, rotate and move. But in the case of uniform electric field, it will just rotate, it won't roll. Let us go to the next part. So torque on electric dipole based upon this one question is there. Two equal and opposite charges, 2 × 10⁻10 coulomb, are placed at distance of 1 centimeter forming a dipole and are placed in an electric field of 2 × 10⁵ Newton per coulomb. The maximum torque on the dipole. Okay, so before I start taking this question, we got the value of tau as Pe sine theta. I'm talking about the magnitude. So its magnitude what was Pe sine theta. So since sine theta is there, we can very clearly see that if theta is equal to 0, then torque also will be 0, isn't it? That is called as the minimum torque. Not only 0, even at 180 degree. Even if theta is equal to 180 degree, sine 180 is 0. So torque will be minimum. If theta is 90 degree, then sine theta is 1. So torque maximum will be equal to P into E. So since they have given the word maximum torque. So what is the meaning of maximum torque? PE. Because theta will be 90 degree obviously. So if torque is equal to PE, we can easily find PE here because P is Q into 2D. QD is given as, Q is given as this. That is 2 into 10 to the power minus 10 D. Q into 2D. That is the distance is given as 1 centimeter. So 1 into 10 to the power minus 2 and electric field is given 2 into 10 to the power 5. So when you solve this, 2 2s are 4 and minus 10 minus 2 is minus 12, 5 minus 7. So correct answer is 4 into 10 to the power minus 7 Newton meter. Simple question actually. So let us go to the next question now. Next topic actually, electric flux. So what is electric flux? Now electric flux is the number of electric lines of forces. You have learnt about electric lines of forces just before some time. How many electric lines of forces are passing normally through an area? So suppose I have this area, the screen I have. How many lines are passing normally through it? Like this. Not in some angle. It should pass normally through it. That many electric lines of forces will become its flux. As simple as it. So what is electric flux? I will say it is, I'll write, it is the number of electric lines of forces passing normally through an area. Passing normally through an area. It is represented by phi. The denotation is phi. So mathematically, phi is equal to E dot dA. That is E dA cos theta. So electric flux is called as electric flux because we also have magnetic flux. So phi E they will write. So electric flux is equal to E dA cos theta. It is a dot product of electric field and area vector. dA means area vector. Remember this. What is the meaning of area vector? If I have some area vector is the line which is perpendicular to it. If this is the area A, then this will be dA, which is any vector perpendicular to the area. So E dA cos theta is the electric flux equation. Next, we have in this topic Gauss theorem. Gauss just gave another expression of electric flux. So what did he say? That if you want to find electric flux by just knowing the electric lines of forces, you take a Gaussian surface. So what he said, suppose I have a charge plus Q. So I can have a charge or I can even have a system of charge. So if I have a charge or system of charge, then if I draw a Gaussian surface around it, 1 by epsilon naught times of how much charge is enclosed in the Gaussian surface, that would be the flux. So as simple as it is. So if I want to write a definition, it is this, I can write like this: surface integral of electric field, surface integral of electric field. Now why I'm writing surface integral of electric field? Because it is E dot dA through any Gaussian surface, through any Gaussian surface is given by 1 by epsilon naught times the charge enclosed, obviously by the Gaussian surface. So phi, which is equal to E dot dA, that will be equal to 1 by epsilon naught times of charge Q. That is what is Gauss theorem. It's very simple, that the electric flux will be the 1 by epsilon naught times the net charge enclosed. I'm again saying net charge. You may have 1, 2, 3, 5, 10. So if I place one other charge minus Q, and if I ask you what is the flux, you will say 0, because plus Q minus Q net charge is 0, isn't it? So you must see what is the net charge enclosed and then decide how much flux will be there. Let us go to the next page. Yeah, I have a question based upon this. Yeah. So which statement is true for Gauss law? So based upon Gauss law, they are asking, out of this 4 statements, which statement is true? The first statement is all the charges, whether inside or outside the Gaussian surface, contribute to electric flux. Definitely not true. Why? Because only the charge which is present inside the Gaussian surface will be considered. I hope you remember that. Electric flux depends upon the geometry of Gaussian surface. Definitely not. Whether we're taking Gaussian surface as cylindrical surface, circular surface, I mean spherical surface or cuboidal surface, everything will give you same flux. Gauss theorem can be applied to non-uniform electric field. No, it is applicable only to uniform electric field. So what is remaining? Remaining is electric field over the Gaussian surface remains continuous and uniform at every point. Very correct. So a simple question, just based upon the knowledge of electric flux and Gauss theorem. If you know Gauss theorem well, this question can be easily taken. Go to the next question. So a charge Q is placed at the mouth of the conical flask. Very beautiful question this is. The flux of the electric field through the flask is how much? So what they're telling, take a conical flask. By now, you know what is a conical flask. Yeah. And they're saying in this conical flask, plus Q is present somewhere here. Charge Q actually. Charge Q is present on the mouth. So what is the flux of electric field through the flask? Through the flask, how much electric field is there? Okay. So flux, how much flux is there? So flux, we know very well, is the 1 by epsilon times of Q. But if it is present inside it, it is present on the mouth. So first I have to make a symmetrical condition. So when I make a symmetrical condition, I must place another flask laterally inverted over this like this. Then it becomes equal now. So now plus Q came in the center of these both. So it will share half of the total flux and it will share half of the total flux. And we know very well what is the flux. Flux is equal to Q by epsilon naught. So through any one of the flasks, it will be 1 by 2 times of Q by epsilon naught. That is Q by 2 epsilon naught. So this answer is correct. I hope you're understanding this, that to find this kind of question, remember that whenever you are learning about the electric flux through any surface, the charge must be in the center of it. Otherwise, if it is at one corner or above or below, you must consider it. That this concept will be very clear to you when I go to the next topic, that is flux through a cube, because this place you will understand very deeply about how the flux changes if the position of charge changes. If we know very well, if we have a cube like this, and if I say you what will be the flux if a charge is placed inside the cube, you will be saying very comfortably, yeah sir, we know it will be 1 by epsilon times of Q. If Q charge is present, you will say phi is equal to Q by epsilon naught. You are absolutely correct. You are absolutely correct. But this is for the total cube, phi for the full cube. If I ask you what is the flux through one of the face, through each face, then what you will say? Because listen to me very carefully, guys, very carefully, that at the center the charge is present, so the flux will be equally distributed. So how many surfaces a cube will have? I hope you know, 6, right? So 1, 2, 3, 4, 5 and 6. So 6, each face will give 1 by 6 times of the total flux. So it will be 1 by 6 times of Q by epsilon naught. So if you have a charge at the center, then the flux will be Q by epsilon naught, total flux of the cube, and each face will get 1 by 6 times of Q by epsilon naught. There is a possibility that this charge is not in the center and it is present in one of the faces here, on the face, this Q. Then what will happen? Will it remain same Q by epsilon naught time? Q by epsilon naught? No. Will it remain same 1 by 6 Q by epsilon naught? No. It will change. How it will change? We need to draw a surface. I should say, we need to draw symmetrical surface. This should be coming in symmetry. For that, what I will do? I'll just place another cube like this. Now it becomes symmetrical. Since it is in the center, it will share equal. So phi of the cube, each cube I should say, because 2 cubes are there now. So phi of each cube will become half times of Q by epsilon naught. And now if I ask you, what is the flux through each face? Each face of any cube. See what will happen? The face through which the cube is touching, that will be neglected because that's not participating. From there only charge is coming out. So in one cube, how many faces are left? Out of 6, if 1 is removed, 5 are left. So it will be 1 by 5th of the total thing, Q by epsilon naught. So it is equal to 1 by 2 epsilon naught. So it will be 1 by 10 Q by epsilon naught. So remember that if you have the charge present at one of the faces of the cube, then the flux through each cube will be Q by 2 epsilon naught, same like that last question, conical flask. And the flux through each face will be 1 by 10 times of Q by epsilon naught. These questions are very common in board examination also. So next, if you see, I have a cube and I am placing the charge at one of the edges, suppose somewhere here. Then what you will do? Once again, I have to make it to come in symmetry. So for that, I'll start placing various imaginary cubes, making it to be in the center of this. So I think if I place 4 cubes like this, it will come in the center. I hope you're able to imagine. So I'm placing 3 more cubes apart from that original cube. So phi through each cube will be 1 by 4 times of q by epsilon naught. I hope you're understanding this. Very simple. So 1 by 4 times it will become. And now you see in each cube how many faces are occupied. If this is attached here, this face, I should take some other color. Yeah, this face as well as this face is occupied. So remaining only 4 faces are remaining. Out of 6, 2 are occupied. So only 4 is remaining. So phi through each face will be 1 by 4 times of 1 by 4 q by epsilon naught. So through each face I am going to get 1 by 16 times of q by epsilon naught. So if we have a cube and the charge is at the center, the flux through cube was q by epsilon naught, and flux through each face was 1 by 6 times of q by epsilon naught, and similarly it changes. What if the charge is present at one of the vertex? Take it as a homework. Do it by yourself. Try to find how many cubes will be requiring to make it come in symmetry. After you find that, you tell me what will be the phi of each cube, and then one hint I'll give you, that since it is present here, 3 faces are occupied, this one, and this one. So it will be, each face will have 1 by 3 times of whatever phi you get for the each cube. I give you a hint now. So you can just solve it and put in the comment box. Let me see how many of you could solve it by yourself. Fine. So we came to know how the electric flux will change for different cube conditions. Now let us go to the question based upon it. A point charge plus q is placed at the midpoint of a cube of side L. The electric flux emerging from the cube. See, very simple. They have told the charge is at the midpoint of the cube. So if this is the cube and the charge is present in the midpoint, somewhere in the center, then obviously the flux through the cube will be q by epsilon naught only. Q by epsilon naught, nothing. Yeah, if it would have been at some face or in the corner or in the edge or in the vertex, then we will have a, solving of that. Or if they would have asked you flux through each face, then it will be 1 by 6 times of q by epsilon naught. But they've asked you flux through the cube, obviously it will be q by epsilon naught. Simple question. Next question. Yeah, next we are going to learn about the last topic of this chapter. Finally, we came to the end of this chapter. That is the application of Gauss law. So we are going to see what are the different applications of Gauss law. So Gauss law is used for basically 3 applications in your 12th standard. One thing is to find the electric field through an infinitely long straight current carrying, straight charged wire. So infinitely long charged wire. You can find what is the electric field for an infinitely long spread charged sheet, and you can also find for a thin spherical shell. But now in the revised syllabus, because I am doing this only for the term 1 syllabus, we have only straight wire and a charged sheet, and we will learn about it. So if you have an infinitely long charged wire like this, I have a wire very long, infinitely long, and charged also. So like something like this, plus, 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 like this. If you want to find what is the electric field of this wire at any point, distance of r, yeah, I can find that by drawing the Gaussian surface. I should draw the Gaussian surface having the cylindrical Gaussian surface at, having cylindrical and radius r. So this you have already done it. And finally, if you see what will be the electric field which you will be getting, electric field due to the straight wire which has charge, and obviously if it is a linear charge density, it will be having lambda, that is lambda is equal to q by length L. So E would be equal to lambda by 2 pi epsilon naught r. Remember this, lambda by 2 pi epsilon naught r. If it is a positive charge plus q, obviously the direction of the electric field will be in the same direction of radius, that is outwards. And if it is for the minus q charge, then it will be lambda by 2 pi epsilon naught r and minus r cap. This shows that it is inwards towards the wire. So please note this. I can also write this electric field in terms of k. It will become equal to 1 by 4 pi epsilon naught. This is I'm writing 4 pi. It is 2 pi. So I'm writing it as 4 pi. I have to multiply 2 above. So it will become 2 lambda by r. And obviously r cap is there. So E vector. So I hope you're understanding what I'm trying to write. So E vector will be 1 by, because sometimes if you bring in this part, we can write k into 2 lambda by r. So very easily we can solve. We know the value of k. Instead of writing epsilon naught, which is 8.85 10 to the power minus 12, k is 9 10 power 9, easy to solve. So we can even use this if it is required. That is how we can find the electric field due to a infinitely long charged wire. Next, we have the application of Gauss law, the second application. We can find what is the electric field due to a infinitely spread charged, thin charged sheet. Suppose I have something like this. So I have a charged sheet like this, maybe positively charged or negatively charged, completely depends. And we want to find what is the electric field due to it at any distance r, again some distance in front of it. So I will draw once again a cylindrical Gaussian surface, and these things you would have done, and you would have also found out what is the electric field, and you should remember, because very important, that is sigma by 2 epsilon naught. Sigma is the surface charge density, q by a or dq by dA. So electric field due to a charged sheet of having a surface charge density of sigma, the electric field will be equal to sigma by 2 epsilon naught. And obviously the electric field direction, it will be normally outwards when, if the charge is positive, and it will be normally inwards when charge is negative. So I hope you have understood this, and it's very simple to remember. For the case of infinitely long straight wire, electric field is lambda by 2 pi epsilon naught r, or k into 2p by r. And if it is for a sheet, it is sigma by 2 epsilon naught. Now we are going to see something very important from this topic, which many students will not mind, and they'll forget this. I have seen questions coming from this area. Even in Cbse sample paper, one question is there based upon this, what I'm going to teach now. So please pay attention. We are in the last topic. Hold with me for another 15 minutes. I'll be done. Believe me. So now, if I have two infinitely long plane charged sheet, for example, I have one sheet like this, and I have another sheet like this, and I want to find the electric field in all the regions. I want to find it here, I want to find it here, I want to find it here. That is, I want to find electric field outside the plates, I want to find electric field inside the plate. What will be the electric field? So I have two conditions. I can have similar charged plates having similar charge densities, that is, here also plus and here also plus, having charge density of sigma 1 and sigma 2. I mean dissimilar charge densities but same sign. And we can assume that sigma 1 is more than sigma 2, that is, charge density of first plate is more than charge density of second plate. If that is true, let us see the electric field. We know very well by now, positive charge, electric field outwards like this. Say a positive charge, electric field outward like this. This I'm writing it as E1, this I'm writing it as E1, this I'm writing it as E2, this I'm writing it as E2. Very clearly you can see from this diagram that in this zone, first plate is having electric field here, second plate also will have in the same direction here only, E2. So net electric field E will be equal to E1 plus E2. And you know very well what is the value of E1? Sigma by 2 epsilon naught. So it will be sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught In simple words, net electric field will be equal to sigma 1 plus sigma 2 divided by 2 epsilon naught. This is the value of electric field on one of the sides. If I see at this side, the same thing will come. See, E2 is this side, again E1 will be this side, and the net electric field E on this side will be equal to E1 plus E2. And how much it will be? E1 is sigma 1 by 2 epsilon naught. E2 will also be equal to sigma 2 by 2 epsilon naught. And finally, same like the previous one, sigma 1 by plus sigma 2 by 2 epsilon naught is the electric field. So when you have two infinitely spread charge sheets having different charge density, outside the plates we will have the electric field of sigma 1 plus sigma 2 by 2 epsilon naught. In the center it's very important. So now even in this side, E2 is this side, net field will be where, whether it will be E1 minus E2 or E2 minus E1. Very simple. I have given the condition here, sigma 1 is more than sigma 2. So obviously E1 will be more than E2, net electric field will be E1 minus E2. So E will be equal to, what is E1? Sigma 1 minus sigma 2 by 2 epsilon naught. This is the value of electric field due to two infinitely charged sheets if it is present and between them. Next condition we have that I have two sheets, but now they have dissimilar charge. So let me make like this. One sheet like this having positive charge density, another sheet like this having negative charge density. So sigma 2, sigma 1, I should write minus sigma 2, and once again I am taking sigma 1 is more than sigma 2. I mean charge density of first plate is more than second plate. So here I will be having outward electric field E1, here also I am having outward E1. For E2 I will be having inwards towards E2 like this, and obviously like this. So here also E2 will be going in this direction, and E1 in this side will be going in this direction. I hope you are understanding this, because E1 is outwards, E2 towards the plate. So if I want to write what is the electric field on the left and right hand side, see very clearly we can see net electric field E1, E2. E1 is more than E2, so E1 minus E2. So how much it will be? Sigma 1 by 2 epsilon naught minus sigma 2 by 2 epsilon naught. So net electric field will be equal to sigma 1 minus sigma 2 by 2 epsilon naught. Similar way, you can find for this side, you will get E is equal to, since E1 is bigger, E1 minus E2, and same sigma 1 minus sigma 2 by 2 epsilon naught. About the center. About the center, if you see, both sides, both things are going in the same direction. So net field E will be equal to sigma 1 plus sigma 2 by 2 epsilon naught. Opposite to what we have seen in the previous slide. In the previous case, we saw that on the left and right hand side, we had E1 plus sigma 1 plus sigma 2 by 2 epsilon naught. In center, we had sigma 1 minus sigma 2 by 2 epsilon naught. Here it is opposite because the charge of the plates are opposite. One more condition is possible, that the charges are same. So now what I am doing, I am keeping the charge to be same. So I have these two plates, one plate here, one plate here. I mean, they are dissimilar charge, but I'm talking about charge density is same. So let me assume like this, minus sigma plus sigma. Interesting, let us see what happens. So E will be acting in this direction, E will be acting in this direction. Since it is this thing, E will be acting towards the plate, that is E and E here. I'm not writing E1, E2 because it is same sigma. So here also E will be coming, and I'm very sorry, E will be coming in this direction, isn't it? So E will be coming in this direction because for negative side I'm talking, and same way for positive side, E will be going in this direction. So if you see at this end, net E will be equal to E minus E. Net E will be E minus E, that is 0. Same way here, net E is E minus E, that is 0. What I'm coming to say, if you have two plates which are dissimilar, it's something like a capacitor or something like a two charged plates, like when you are trying to keep them charged. Both the sides, outside the plates, we have no electric field, it is 0. Inside the plate, it will be E is equal to E plus E, that is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that will be equal to sigma by epsilon naught. So electric field between them, very important thing I'm telling you, you may have questions based upon that. If there are two charged plates, then the electric field outside them, if the surface charge density is same, then it will be 0 outside the plate, and inside the plate it will be sigma by epsilon naught. I hope it is clear. And then we come to one question of Gauss law, and that question is, there are two parallel large thin metal plates having equal surface densities, and they have given value of that of opposite signs. The electric field between those sheets. See, this question once again I have taken from the sample paper, from the Cbse sample paper, believe me. So very simple question this is, if you know the concept, because they have given two parallel thin metal sheets have equal surface densities. When they told it is equal surface densities and they have asked you between the plates, obviously write E is equal to sigma by epsilon naught. Story is over. Sigma is given 26.4 10 to the power minus 12, and we know very well that epsilon naught is 8.85 10 to the power minus 12. These two will get cancelled approximately 3 times. This is the answer. Done. See how simple the question is. If you know this concept, the previous slide, I taught you that electric field between two charged, that is dissimilar, opposite signs they have given here. Two parallel charge plates have equal surface densities of opposite signs. This question was there in the sample paper. So what I'm coming to say is, read the question very carefully. And questions will not be very tough, believe me, if your concepts are cleared. So in this lecture, like up to whatever I've taught, I try to make like all the things bit easy. I try to cover each and every concept without leaving a single thing. Believe me, I've covered each and every topic from this chapter. Nothing I have left. And from almost each topic, I tried to solve at least 1 or 2 questions. So you have seen some 15-16 questions from this chapter, which can come in the board examination, and you have learned each concept. One more thing I will say you, not only this video is for today's session, it will be saved in the YouTube channel. Before your examination or whenever you want to see, you can open it up, go through everything once again, take proper notes, and it will be helpful for the examination. So I hope I could make your things clear. And as I said you, today there was some issue in the network, the power. So only it happened in 2 sessions. Otherwise, every day at 6 p.m. we will meet here for the coming 6 days, where we will be learning all the chapters day by day. And by 23rd of this month, I hope you will be knowing all the physics chapters deeply, if you are really coming and attending it. One thing, whatever I have taught, you have to open the book at the end and go through all the concepts. Then only it will be clear. So I hope everything was clear. So bye-bye guys, take care. If you have liked this video, then please like the video in the YouTube also. Press the bell icon, subscribe the channel. Take care, bye-bye, thank you.